Hey everyone, welcome back. In this lesson we're going to talk about seasons. So in the previous lesson we talked about weather and climate, and we got just a tiny bit into seasons at the end of it, but then we saw this diagram that had quite a lot of stuff in it. So we're going to address some of the things that are in that diagram, and we'll get a more thorough introduction to the reasons for seasons. So for those of you that have forgotten, or maybe it's been a little while since we or since you watched the previous lesson, here's the diagram that we sort of left off with, and so we're going to break down some of the things in this diagram in this lesson. Now we're not going to pay a ton of attention to these things up here, the North Celestial Pole. We won't really worry about that too much. We won't worry about the South Celestial Pole. We'll talk a little bit about this ring that goes around the middle called the ecliptic. We also won't worry about the celestial equator, I think, in this lesson. It's not the most important part of what we're going to be discussing, so we're going to leave it out. We will talk about the ecliptic a little bit at some point, and this bit about orbit direction, but I think it's safe to say that we won't be discussing the South Celestial Pole, the North Celestial Pole, or the celestial equator. So don't worry about those things. We'll talk a little bit about axial tilt. We'll talk about the ecliptic. Whoops. We'll talk about the ecliptic, and we'll bring in a little connection to the orbit as well when we're discussing the ecliptic. But aside from that, you don't have to worry too much about all the things on this slide. So, as promised, we are going to talk about axial tilt, but first we're going to discuss the difference between rotation and revolution. So, something that a lot of young people tend to confuse the first time that they hear these words is the difference between rotation and revolution. So we know that the Earth spins around its axis once per day, and this is responsible for the day-night cycles that we experience. This is rotation. This is the Earth spinning by itself, and it has very little to do with the sun. I mean, of course, the sun's presence is why we have day and night, but if you took the sun away, Earth would keep rotating around its axis in this way. So let me just draw a little sketch just to sort of highlight the difference between rotation and revolution. So let's say we've got the sun right here, and we've got the Earth right here. This is not drawn to scale because the Earth is not that big in relation to the sun. But anyway, rotation is when the Earth spins around its own axis. So this kind of spinning action is the Earth's rotation. It's rotation about its own axis. Revolution, so this part, Earth revolves around the sun once a year. Revolution is this motion where it goes all the way around the sun and comes back to where it started. So that's the difference between rotation and revolution. Rotation is responsible for day and night, but revolution, combined with this term up here, axial tilt, revolution and axial tilt together are responsible for seasons. So we're going to dive into this a little bit and explore some features of the planet that are related to these concepts. So an important thing to note is that when the Earth spins, let me see if I can draw this out. This would be a lot easier to show on video, but that's not the way that these lessons are set up. So I'll show you guys during our next live class, I guess, or once you guys have all seen this video, then we can talk about this in class as well. But so basically, I'm going to draw out sort of the easy way. Hang on, let's try that again. I'm going to draw out the easy way that you could picture the Earth rotating, and then the way that the Earth actually rotates. So, if the Earth is moving in, let's say, this direction, all right, then it would be easy if its rotation was straight up and down. So if I draw lines for its axis in purple, let's say, if I draw lines for the axis of rotation, it would be nice and convenient if the rotation was this straight up and down axis, and then the Earth could rotate like this around its axis while it's moving around the sun in that direction. What actually happens, though, is that while the Earth is moving in this direction, let's say, the axial tilt, so the position of the axis, is not this straight up and down thing that we would like it to be. Instead of being here and here, the axis is more like here and here. So instead of spinning the way this thing shows, it spins more like this. So kind of on an angle with relation to the way it's moving around the sun. It's at this little bit of an angle. So like if we treat, so let me get rid of those other lines just to clear it up so we can see that we've got this little, instead of it being straight up and down, it's tilted over this way and tilted over that way. So the whole planet is a teensy bit leaning towards its side. So basically the way you could think of it is if you have like if you have a top, you know, there was a spinning top, and you put it on a floor, that floor would be like where the Earth orbits around the sun. So the direction that Earth moves in, you could draw in like a little short on space on this slide. So let's see if we can make this work. So we could draw in like a little floor and say that if the Earth sits on this floor, then it's moving around the sun parallel to that floor. But its rotation isn't like this. Instead, its rotation is, let's see if I can get rid of just that. Instead of that, Earth's rotation is more like that, on an angle. So it's a little hard to draw, but I hope you're getting some sort of an idea from it. We're going to see this with more professional pictures than the ones I've just drawn in here. But the idea is that the Earth doesn't spin straight up and down on its axis. It's tilted a little bit in one direction. And the angle of that tilt, so if you look over at this guy up here, we would have thought that the simple case would be if the axis was straight up and down, something like that. But these red arrows are showing that it's tilted a little bit to one side and tilted a little bit to one side down there as well. And that angle of tilting is this right here, 23.5 degrees. So the angle of tilting up there from straight up and down to what the axis is actually, the direction the axis is actually pointed in, this angle in between is 23.5 degrees. So basically what this means is that the way that the planet spins isn't aligned with the way it orbits the sun. And by aligned, I don't mean in the same line. That's kind of bad wording. I mean, it's not perpendicular. It's not like at right angles to the direction in which it orbits the sun. That would probably make some things easier to understand, you know, when we're looking at the motions of stars and stuff, if the direction of rotation was kind of had some connection to the way it moves around the sun, but that's not the case. So we have to deal with this awkward 23.5 degree tilt instead. But we should be grateful for that tilt because that's the reason that we have seasons. So let's get into how this tilt is related to seasons. Basically, the fact that the planet's tilted like this means that these axes here aren't actually straight up and down. At some times in the year, this northern axis is tilted a little bit towards the sun, and at other times of the year it's tilted away from the sun, depending on where it is in its orbit. So let's take a look at some more professionally done diagrams in the slides to come. So here you can see a clearer version of what I was trying to draw on the previous slide. So this is this yellow line right across the middle here. This is the ecliptic, which we saw at the beginning of this at the beginning of this lesson. So that's the flat kind. If you picture it like a flat sheet, and the Earth's orbit is right in that sheet of like a big sheet of paper. You could draw the Earth's orbit right into that sheet. It makes this completely flat thing, which is what we call a plane. Now, it would be convenient if the Earth's rotation about its axis was perpendicular to that plane. So if it was this straight up and down compared to this yellow line right here. But that's not what we see. We see this red line as being the tilt of the Earth's axis. So the Earth's axis of rotation, this thing right here, the Earth's axis of rotation, the line around which the Earth spins, is tilted a little bit away from this straight up and down vertical perpendicular line right here. And that degree of tilt, that angle of tilt, is 23.5 degrees. So what this means is that at different times of the year, as we said a couple of slides ago, the northern hemisphere is tilted towards the sun, which means that it's summer. And at other times of the year, the same part of the planet will be tilted away from the sun because it's in a different position in its orbit, and that's when we get winter. So we'll see more diagrams of this shortly. So this is a really good diagram to sort of explain what's going on. So notice that the axis is always pointed in the same direction. The direction of this axis that's running through the whole planet is the same here and here and here and at the top there. It's always pointing in the same direction. What changes is the Earth's position relative to the sun. So sometimes you'll have this is the North Pole, the northern part of the axis of rotation. At this point of the year, so December into January, it's tilted away from the sun, which means that it's not getting as much of the sun's light and heat. That's when we get winter in the northern hemisphere. But at the same time, the South Pole is tilted towards the sun. So that's when it's summer in the southern hemisphere. So for all the penguins, it's summer in late December going into early January. And, so this is the warmest time of the year for the southern hemisphere. And then as the Earth moves around its orbit, it goes in this direction like this. So as it moves around its orbit, we get to a point where neither the North Pole nor the South Pole is tilted towards or away from the sun. They're both an equal distance from the sun. And that can be kind of hard to draw, so this is the way that it's commonly shown, and it requires a little bit of imagination on your part to really understand what's going on. But so basically at this point, neither hemisphere is tilted towards or away from the sun, and that basically means that this is when we transition from winter into spring, or from summer into fall or autumn, depending on where you are in the world. So you start out over here, let's say, winter in the northern hemisphere. Since you guys are all, to my knowledge, in the northern hemisphere, and I'm in the northern hemisphere as well, and most of the world's population is in the northern hemisphere, we'll just talk about that. And then, if I'm saying it's winter, then I mean the opposite season for the southern hemisphere. So we'll just talk about the northern hemisphere for the time being. So if it's winter over here for all of us in the north, then as you move this way around the orbit, we get to a point where the North Pole is no longer tilted away from the sun, but it's also not tilted towards the sun. So this is when it transitions from winter into spring. And then as the North Pole gets tilted more and more towards the sun, that's when we get over here, where it's tilted the most that it'll be over the course of the year, tilted towards the sun. That's when it's summer in the northern hemisphere. We get nice long days and warm weather. And then it continues around the orbit until it's not tilted towards the sun, but it's also not tilted away from the sun. And then that's when we transition from summer into fall or autumn. And then we continue back to where we started, where instead of being neither towards nor away from the sun, now it's tilted away from the sun. The North Pole is tilted away from the sun. And then, of course, if you look, you could do the same thing for the South Pole, that here it's tilted towards the sun, so it's summer. You go this way, it's fall. You go this way, it's winter. You go this way, it's spring, and then summer again. And you can keep going around like that. Yeah, so that's basically the reason for the transition between the different seasons is due to this tilting of the axis. You can maybe see that if we didn't have any tilting, if the axis was like this instead, then it's never going to be tilted towards or away from the sun. It's always going to look like this, like this, like this, and like this, roughly speaking. And so we wouldn't experience any seasons in any part of the world because nothing really changes going from one time of year to another. Now, it's important to understand that seasons are experienced very differently in different places. So regions close to the equator, which is the circle that divides the planet into a northern hemisphere and a southern hemisphere, if you live near the equator, which many of you do, then the seasons don't assert themselves that much. And what I mean by that is that you don't experience huge differences between the seasons in different times of year. That you might have winter where it's 20 degrees outside, and then summer where it's 25 degrees outside. It doesn't really change the way that you live your life. Now, granted, places in tropical regions, equatorial regions, these hotter parts of the world, don't tend to have cold and hot differences over the course of the year, but they do tend to have wet and dry differences. So that does change, but temperature, speaking strictly about temperature, equatorial and tropical regions don't see significant changes in the temperature or, as I've noted right here, the number of hours of daylight over the course of the year. So basically what that means is, for those of you that have always lived near the equator, the sun will rise at around 6 in the morning, let's say, and set around 6 in the evening. And if you don't live exactly on the equator, then it'll change a little bit over the course of the year. So maybe in the summer, the sun rises at 5 instead of 6, and then in the winter it rises at 7 instead of 6. And things like that. So you might get slightly longer days in the summer and slightly shorter in the winter, but the farther you go away from the equator, or the closer you get to the poles, then one, the temperature differences start to be pretty drastic, pretty significant, and also the hours of daylight change dramatically when you get close to the poles. So you'll get areas of the world where when it's winter, there's barely any sun at all. It rises for a couple of hours, if that. Or, where I live, it's not that extreme, but it is like in the winter you'll get something like maybe 10 hours of daylight out of 24. But then in the summer you get like 14. So there is a pretty drastic difference that in December, if you go out for a walk at 5 p.m., it's pitch black. It looks like night. But then in July, if you go out for a walk at 9 p.m., it looks like 4 o'clock in the afternoon because the sun is still up. So those things do change drastically, especially near the poles. And like I said, daylight hours vary significantly depending on your location. So there are 5 major, what we call circles of latitude, that correspond to some very specific details about how the Earth is oriented in space. So like the direction that Earth is pointed in and how it moves around the sun and things like that. First, before we get into that, we're going to talk about what this word latitude means, because just like rotation and revolution, people tend to get confused between latitude and longitude. So before I show you a diagram that explains the difference between latitude and longitude, I'm going to list the major circles of latitude themselves, just so that you can, maybe you've already heard of all of these, or at least hopefully this first one. And and we'll talk about these 5 later on in the presentation, but here are their names. So the 5 major circles themselves are the equator, the Tropic of Cancer, the Tropic of Capricorn, the Arctic Circle, and the Antarctic Circle. Now those aren't in order from north to south or anything like that. The equator is, if you were to look at a world map, chances are the equator is dead center. Then the tropics are a little bit north and a little bit south of the equator. And then these polar circles are really far north and really far south. So this is like bang on in the middle of the map. These two are kind of in the halfway between the, not actually halfway, but for simplicity's sake, halfway between the middle and the top. And then these ones are way up near the top or the bottom of the map. So before we continue into examining this further, let's just take a moment to discuss the difference between latitude and longitude. So lines of latitude are, if you ever look at a map, maybe you guys could pull one up now, you have these lines, these horizontal lines that run left to right or right to left or east to west, however you wish to describe it. The lines running east to west, these are lines of latitude, and the equator is this one in the middle that divides the Earth into a northern hemisphere up here and a southern hemisphere down here. Longitude, lines of longitude on the other hand, they run north to south. They're these vertical lines that go around the planet. And the difference between lines of latitude and lines of longitude is that with lines of latitude, the equator is the longest one. So you could describe it as the longest line of latitude, or the biggest circle of latitude if you picture the Earth being a globe. But for lines of longitude, they're all the same length. So in order to choose a special one, we had to sort of pick one ourselves because the Earth wasn't giving us a special one. And so we've picked this one that runs through Greenwich, England, and that's called the prime meridian. So if you're ever looking up the geographical coordinates of a place, when we're talking about how many degrees north or south we are, we're talking about relative to the equator. So something up here would be, let's say, 35 degrees north of the equator, whereas something down here might be 35 degrees south of the equator. But when we're talking about how far east or west something is, we're talking relative to the prime meridian. So we'd be talking how many degrees east or west of this particular line, which isn't special, we just chose it to be special. So we could say this line is 0 degrees east and west, and then any other line around the planet will be some number of degrees east or west of this line right here. So for the equator, it's actually a special line that's different from the other lines of latitude. For lines of longitude, we just picked this special one. Now, the ones that we're concerned with in this lesson are lines of latitude, so we're not going to worry about lines of longitude too much. So the major circles of latitude themselves, the 5 major ones, are the equator, the Tropic of Cancer, the Tropic of Capricorn. That's a typo, but in fairness, this isn't my picture. Equator, Tropic of Cancer, Tropic of Capricorn, the Arctic Circle, and the Antarctic Circle. So you don't really have to worry about the stuff that's going on over here too much, but do take a brief look at some of these numbers that you see on the right side here and on the top and bottom. So we define the equator to be at 0 degrees latitude. So anything north of that is going to be some number of degrees north of the equator, and anything below it is going to be some number of degrees south, up to a maximum of 90. So the North Pole is the farthest north you can go. It's 90 degrees north of the equator, and the South Pole is 90 degrees south of the equator. Now, don't worry too much about the numbers after the degrees. So don't worry too much about like the second number for all of these. That's pieces of a degree. So we'll really just kind of restrict ourselves, just for simplicity's sake, to the first number in each of these. So we've got 66 degrees, 23 degrees, 23 degrees, and 66 degrees. Just to let you guys know, basically each degree can be divided into 60 little pieces, just like an hour is divided into 60 minutes. And then we actually call these arc minutes with a little tick mark instead of a degree symbol. And so basically this is saying 66 degrees and then 34 pieces, 34 minutes of a degree. So 34 minutes, if you think in terms of time with minutes and hours and stuff, 34 minutes is about half an hour. So 34 minutes here is about half a degree. And same thing with the 26. If you think on a clock, 26 minutes is about half an hour. So 26 arc minutes is about half a degree. So we could say that this is 66.5 degrees, 23.5 degrees, 23.5 degrees, and 66.5 degrees. But of course, the differences are that like the Arctic Circle is 66.5 degrees north of the equator, but the Antarctic Circle is 66.5 degrees south of the equator. So that's something to keep in mind. If that didn't make sense, don't worry about it too much. This is just sort of an introduction to how these things work in case that's something that you're interested in knowing. So now let's talk about each of the lines themselves. So the first one is the equator, which is bang on in the middle of the planet if you look at most maps, pretty much. The equator is halfway between the North Pole and the South Pole, and it basically divides the planet into two hemispheres, two halves, the Northern Hemisphere and the Southern Hemisphere. It's the circle of latitude, so we have these 5 major circles of latitude. It's the circle of latitude that's defined to be at 0 degrees, 0 degrees north or south. We sometimes call circles of latitude parallels of latitude because they're all parallel to each other, which basically means that lines of latitude never touch. But lines of longitude, they all join up at the North Pole and at the South Pole. And of course, if that's something that you'd like to talk more about, we can talk about it on Tuesday. But basically, lines of longitude all converge. They all meet together at the North Pole and at the South Pole, but that's not the case for lines of latitude. And since they never touch each other, they're called parallels, because that's what it means. Parallel lines never touch. So a special thing about the equator, aside from the fact that it's actually the biggest circle of latitude, like if you were to measure out the distance walking around the planet, the longest distance that you would measure is at the equator, strictly speaking, latitude-wise. And so the sun is directly above the equator during the March and September equinoxes. We're going to come back to talking about what this word is and what this all means by looking at some pictures a little bit later on. Now the idea is, if you live near the equator, the sun traces out pretty much the same path in the sky every day, all year. It might move a little bit, but it's basically going to be more or less straight up overhead, or a little bit one way or the other, over the course of the whole year. So one, the temperature doesn't change very much, but because the sun is directly overhead, it's beaming down all its rays right over the equator and the regions right around it, so it tends to get very warm. And so that's why regions around the equator and in the tropics in general experience such warm climates. So equatorial regions don't experience warm and cold differences in the seasons because the sun is always beaming down all its rays right into this. It's always concentrated right on the equatorial region. So instead of experiencing warm and cold seasons, they experience wet and dry seasons. Now we move on to the tropics, which are a little ways north and south of the equator. So the tropics are located 23.5 degrees north and 23.5 degrees south of the equator. The one that's to the north is called the Tropic of Cancer, and the one that's to the south is called the Tropic of Capricorn. These are, alternatively, if you don't like those names, you could call them the Northern Tropic and the Southern Tropic. I grew up calling them the Tropic of Cancer and Tropic of Capricorn, but I think I would prefer to call them the Northern and Southern Tropics. But if you ever read a book or hear me or anybody else call them by these names, that's the same thing as those names, if those are the ones that you're more used to. So these lines of latitude, these parallels of latitude, or circles of latitude, if you will, they separate the tropics, so the region of the planet known as the tropics, from the temperate zones. So basically what we have is, we've got the planet that looks like this, roughly speaking. And so then we've got the equator running right across the middle. And so that divides the planet into north and south. We've got north up here, and we've got south down here. Then we've got these tropics, which divide the planet, let's use blue, which divide the planet a little bit further. So we've got a line here, that would be the Tropic of Cancer, and this one down here would be the Tropic of Capricorn. And so then all of this space in here is the region of the planet that we would call the tropics. And the region right on the other side of this blue line would be the temperate zones above this blue line. But those temperate zones don't go all the way to the top and bottom, because that's where we're going to talk about the next thing, which is the polar circles, which go way up there and way down there. But in between them, we have the temperate zones. Now, the thing that defines where the tropics are comes in these last 2 points. So the sun is directly above the Tropic of Cancer, so that top blue line right there. The sun is directly above the Tropic of Cancer on the June solstice. That's another word that we're going to talk about in a few minutes. We talked about, we saw the word equinox. This is a related word, solstice. We're going to talk about that in a few minutes as well. And so it's directly above the Tropic of Cancer on the June solstice, and it's directly above the Tropic of Capricorn on the December solstice. So basically the tropics, this region that I've shaded in blue up here, the tropics are the region of the planet where the sun is directly overhead at some point of the year. So not always, but at some point of the year, the sun is going to be directly overhead a point in this region. And because of the Earth is spinning around its axis, if the sun is overhead right here, then as the Earth spins, the sun is still overhead all the way around over the course of a day, and then over the course of the next few weeks, it starts to migrate back south. So the sun starts out being, let's say, overhead right here on the June solstice, and it'll still be overhead all the way around the planet there on the June solstice. And then as we progress through the summer and into the fall, then in the September equinox, it'll be right on the equator. And then it'll keep moving south until the December solstice, when it's right over top of this blue line. And then it starts to move back up. And on the March equinox, it's back on the equator. And then as you get back to June, then it's back over top of the Tropic of Cancer. That's not the easiest thing to show right now, so maybe that's something that we'll have to talk about more during our next live session on Zoom. Now, before we move on, just this last point right here. So since this is the region where the sun is directly overhead, the directly overhead bit is important because that means it's getting the most direct sunlight. So it's getting a lot of light, but it's also getting a lot of heat out of it. And so that's why the tropics are the region of the planet with really warm climates. And the temperate zones don't really get that. The temperate zones never have, at any point in the year, no matter how clear the sky is, like clouds or not, the sun is never going to be directly overhead. So anyone outside of the tropics is never getting sunlight that's as direct as you could get in the tropics. And so the climate tends to be colder. Now, before we move on to talk about the last one, let's discuss these two ideas, the subsolar point and the zenith. So the first one is the subsolar point. So this is a location on the planet itself where the sun appears to be directly overhead. So if you got the sun right here and you got the Earth right here, the sun's beaming down, but if you were standing right here, let's say, then the sun's clearly not directly overhead, because if I draw in a little person, if you got a little person right here standing on the surface of the planet like that, then directly overhead would be in that direction. We don't see the sun in that direction. The sun's clearly over in this direction, so it's not going to look like it's directly overhead. But if you're standing right here and you look straight up, if you're standing right there and you look straight up, then the sun is directly overhead. So this point where it looks like, let's draw that in red, this point right here where it looks like the sun is directly overhead or 90 degrees to the horizon, that's called the subsolar point. So that's the point that I was highlighting with the laser pointer on the previous slide. That subsolar point moves throughout the year. Sometimes it's up by the Tropic of Cancer, Sometimes it's by the equator, and sometimes it's down by the Tropic of Capricorn, but it's never outside there. So only regions within that area will ever be crossed by the subsolar point, and anywhere outside of it never gets to be crossed by the subsolar point, and so it never gets energy that's as direct as the energy that's within these tropical regions in here. Now the other word here is the zenith. So basically that's the direction that's directly above a person on the surface of the planet. So that's what this diagram here is for, is that if you're standing on the surface of the planet, then the zenith is straight up above you. So for the little purple guy that I drew over here, this purple arrow is the zenith direction for this guy. But for somebody standing right here, then the zenith direction is over there. So basically you could think of it as the subsolar point is a point on the planet where the sun is directly overhead, but the sun being directly overhead means it's at the zenith. So these two words are related. They're not really going to come up in the rest of this lesson, but it's just words that you should know if this is the kind of thing that you're interested in. So now we move on to discussing the polar circles. So this is the Arctic Circle and the Antarctic Circle. So these two circles occur at latitudes of 66.5 degrees north and south of the equator. This respectively means that the first one here corresponds to the first thing there, and the second one here corresponds to the second thing there. So the Arctic Circle is 66.5 degrees north of the equator, and the Antarctic Circle is 66.5 degrees south of the equator. And these separate the temperate zones of the planet from the polar regions of the planet. So if I draw out our little sort of drawing of the planet again, and we put the equator across the middle, so we already talked about the equator. It divides the planet into north and south. But then if we draw in the tropics, so then we got the Tropic of Cancer right here, and the Tropic of Capricorn right here. So the regions inside here, these are the tropics in here. And this is where the subsolar point lives. So the subsolar point, the sun appears directly overhead only within this shaded blue area and nowhere else. Then north and south of the tropics, so in this area right here, are the temperate zones. So this would be the northern temperate zone right up here, and the southern temperate zone down here. Like that. And then beyond that are the polar regions themselves. So we've got the northern polar region up there, and we've got the southern polar region down there. So just the way that the subsolar point lives in this blue area, that the sun only ever appears directly overhead within this region, within this blue region for the tropics, there's a similar way to define where the Arctic Circle and Antarctic Circle go. If you go far enough north or south, then you'll eventually get to a point where there's at least one 24-hour period when the sun does not rise at all. So basically a full day without any sunlight, as well as at least one 24-hour period where the sun does not set, so a 24-hour day. And so those regions occur north of the Arctic Circle and south of the Antarctic Circle. And the positions of these circles, along with the positions of the tropics, are actually directly related to the tilt of the Earth's axis. And we'll see that a little bit later on. But so basically this 24-hour period with no sun or with all sun, these tend to occur on and near the solstices, because that's when the planet is tipped to its greatest extent either towards the sun or away from the sun. If the planet's tipped as much as it can go towards the sun, then you're going to get a 24-hour day. And if it's tipped as far away as it can be from the sun, then you're going to get a 24-hour night. So that's what occurs in these extreme north and extreme south regions of the planet. So let's take another look at this and just plop down where the solstices and the equinoxes go. So let me just advance to the next slide because that's where I have the labels. Bam, there we go. So the solstices and the equinoxes mark these special points during the planet's orbit. The solstices occur in December and June. It's a little confusing that it says December on this side and January on this side and then June and July over there. But there's a December solstice and there's a June solstice. And what that means is that the axes, or that the axis, the North Pole and South Pole, are at their greatest extremes, being pointed either towards the sun or away from the sun. So in December, the North Pole is at its greatest tipping away from the sun, and the South Pole is tipped towards the sun as far as it can go. And then 6 months later, or earlier, in June, the North Pole is tipped as far as it'll go towards the sun, and the South Pole is tipped as far away from the sun as it can be. So this would be periods of the longest day or longest night, depending on where you are in the world. So the longest night in the Northern Hemisphere occurs in December on the winter solstice, and the longest day in the Northern Hemisphere occurs on the summer solstice. The problem with saying summer solstice and winter solstice is that it's only summer or winter for half the globe at that time. So I can't really say, oh, it's the summer solstice in December because, well, it's not. It's the winter solstice for me. But for somebody in Argentina or South Africa, it is the summer solstice. So that's why instead of saying summer solstice and winter solstice, which are more common, I'm saying December solstice and June solstice because those are the same. The equinoxes are related, but instead of being at the most extreme tipping away, this is when there's no tipping towards or away from the sun at all. And this is when the length of the day is 12 hours, exactly 12 hours, everywhere on the planet. There's no longer day in the north, no shorter day in the south, nothing weird going on with the poles with this 24-hour day or 24-hour night. 12-hour day everywhere. That's happening on this equinox and this equinox. And so these mark the start and end of, well, these mark the start of spring and the start of fall, depending on where you are in the world and where the planet is on its orbit. So in September, this would be transitioning out of summer in the Northern Hemisphere towards winter in the Northern Hemisphere. So that means it's autumn or fall. But 6 months later, you'd be transitioning from winter in the Northern Hemisphere to summer in the Northern Hemisphere. So that's spring. But when it's spring in the Northern Hemisphere, it's autumn in the Southern Hemisphere. And when it's autumn in the Northern Hemisphere, it's spring in the Southern Hemisphere. So instead of saying spring equinox or autumn equinox, we'll say the September equinox and the March equinox, just the same as we did for the solstices. We'll use the months for that. So basically, when you hear first day of winter, first day of spring, first day of summer, first day of fall, things like that, those are relating to when the solstice and equinox dates are. So, for example, the December solstice is usually around December 21st or 22nd or so. So the first day of winter, like officially speaking, is at the December solstice. So if it's on the 22nd of December, then that means December 21st is still fall. And then December 22nd hits, it's the solstice, bam, first day of winter in the Northern Hemisphere. And then 3 months later, in March 20th, let's say, you'll get the first day of spring. So that's the spring equinox. It's a really specific point where for that instant, the day length would be 12 hours everywhere. And then the same thing 3 months later in June, the longest day of the year in the Northern Hemisphere, longest day meaning most daylight hours, that's the first day of summer, and then same deal with fall in September. So this is a picture of what the Earth roughly looks like during the June solstice. So for those of us in the Northern Hemisphere, that would be the summer solstice. So you can see here that if we've got the sun's rays coming from the left like that, then the axis, it might be a little hard to see, so I'm just going to see if I can draw over it a little bit. There's the Earth's axis, there and there. So there's the Earth's axis. So we can see that the North Pole is tipped towards the sun. And so if you look, the Arctic Circle, it's really hard to see like where the actual line is, but if you follow along with this gray line right here, you can see that it intersects the planet right there, and then kind of goes around to like over here somewhere. So right in there, all of that is within a region that's all north of the Arctic Circle. All of that is north of the Arctic Circle, and what's happening there is at this time of year, the sun doesn't set because the Earth is so tilted towards the sun that if you're on a point right over here, 12 hours later, you're just going to be over here, which is still getting sunlight. So the sun will move around the sky. It might get closer to setting, but then it'll come right back up again. So you could start out over here, and then 12 hours later, you're over here, still getting sunlight. And 12 hours later, you're back over here, and you're still getting sunlight. So you've got your 24-hour day. And if you're really close to the pole, then this will actually go on for way more than just the solstice date itself. It will go on for, I don't know how much longer, but it's definitely not just a one-day occurrence. It'll be like on the order of several weeks. Meanwhile, you can see down here for the South Pole that it's tipped as far away from the sun as it can be. So this is winter. This is the depths of winter in the Antarctic. So if you were on a point over here, 12 hours later, as the planet spins, you're going to end up over here, which is still dark. And then another 12 hours later, you're going to be back over there where you started, which is still dark again. So you've got your 24-hour night south of the Antarctic Circle, and you've got your 24-hour day north of the Arctic Circle. One other thing to note here is that here's the Tropic of Cancer, and on the June solstice, the sun's light is bang on right on this Tropic of Cancer, right there. It's hitting directly on the Tropic of Cancer. So this right here, where my laser pointer is, that would be where the subsolar point is on the June solstice. It's right on the Tropic of Cancer. It's getting the most direct sunlight. And then these regions around it are also getting a lot of direct sunlight, sure, but it's right on the Tropic of Cancer, which is well inside the northern hemisphere. So the northern hemisphere is getting a lot more direct light and heat from the sun than these regions down here. So like poor South Africa in June is not getting very much direct sunlight, but these regions further north are getting lots of sun at this time of year. Conversely, if we look at the December solstice, it's the same idea. Hopefully the axis is a little bit easier to see this time, but if not, I will still try to trace over it as best I can. There's the axis right there. And so once again, we can see it's now the same thing as before, but in reverse. So in the north, if you start out over here where my laser pointer is, then 12 hours later, as the Earth rotates, you're over here, which is still dark. And then another 12 hours later, you're back over here, which is still dark. So you get 24 hours of night. And similarly, if you're a little bit south of the Arctic Circle, then you really don't get that much sunlight over the course of the day. You'll get a little bit of sunlight while you're getting some really indirect rays from the sun, because these light rays are not hitting the ground directly. They're coming in at an angle, because the ground level for you would look like that, and this is not a very direct ray of light, because your zenith direction would look like that. So if you were getting direct light rays, the sun should be coming from over there, but it's not. So you'd only be getting very indirect sunlight for not that many hours, and then you're plunged into darkness for the rest of the day. And that's why it gets so cold. You're just not getting enough heat energy from the sun. You're still getting some rays, but they're spread out over such a huge area because they're coming in at such a shallow angle like this that the temperature drops really, really low when you get really close to the poles. So that's why it gets so cold in winter the farther north you go. The equator doesn't really matter. It's still getting reasonably direct sunlight, just as it was on the June solstice. And of course down here with the South Pole, it's the opposite of what we saw before. If you start out over here, 12 hours later, you'll be over here, still getting sunlight. 12 hours later, you'll be back over here, still getting sunlight. So 24 hours of daylight. And the last point with this one, just as similar to what we saw before, here where my laser pointer is the subsolar point, and it's right on the Tropic of Capricorn. So on the December solstice, the subsolar point is right on top of the Tropic of Capricorn, and during the June solstice is right on top of the Tropic of Cancer. Now these diagrams are a little bit misleading because instead of changing the direction where the sun's rays were coming from, all I could find were diagrams where they just tilted the Earth the other way. And so I want to clarify quickly that tilting the Earth is not what happens. If you remember the diagram from earlier, and I'm going to pull it up again in a second so that you can see it again. The axis, if you look at this one, the axis is pointing this way. But then if you look at this diagram, the axis is pointing that way. That's not what happens. That's not the reason for the seasons. The axis is not swirling around, spinning around wildly like that. The axis stays pointed in pretty much the same direction. It wobbles a tiny bit, but nothing like this. Just a tiny bit, and you can't really notice it at all without scientific instruments. So basically, the axis should stay pointed in the same direction. What changes is that at this time of the year, this would be the June solstice, at this time of the year the sun is coming from over here. In December though, the sun is just over on that side because I've drawn this as though the sun orbits the Earth. We know that's not the case. The Earth orbits the sun. So basically what happens is, let me see if I can draw this a little bit more cleanly. So we've got Earth in June, Earth in December, and a sun in the middle. So if we've got our axes like this, then as the Earth moves around the sun like that, and then back around this way, you can see that right here, the North Pole is tilted away from the sun. So that would actually be this diagram right here. But it looks like, if you look at these two diagrams, if you compare them, it looks like it's the axis that's swinging wildly. That's not what's actually happening. If you look up here, it's the axes stay, the axis of rotation stays in the same position. It's the planet that moves. So the sun ends up being basically on the other side. So this diagram, this pair of diagrams is misleading. It's really good for explaining the 24 hours day, 24-hour night, and where the subsolar point is and all that stuff, which is why I use them. But now I want to clarify that it's not the axis that's swinging wildly creating our seasons, it's the Earth's motion around the sun. So I edited these two pictures by reflecting one of them sideways, which I'll show you on the next slide, which would be a more accurate picture of how this should look. So actually, yeah, this was the diagram I was going to bring up that I mentioned a second ago. If you look at this, like the one I just drew on the previous slide, the axis is pointed in the same direction all year long. It's just the planet that's moving around the sun. So at certain times of the year, the North Pole happens to be tilted away, and at other times of the year, it happens to be tilted towards the sun. But the axis itself doesn't change whether it's pointing this way or that way or some other way. So that's not what's going on. It's the axis is always pointed in the same direction, and it's the planet that's moving. So now if I take those diagrams from the previous slide and I reflect one of them to sort of try and recreate this, then we get this. So now we have this. Now you can see that the axis, it might be a little bit hard to see, but I'm just going to try and indicate it with my laser pointer so I'm not messing up where the axis is. So you can see right there is the North Pole, and right down here is the South Pole, and it's pointing in the same direction over here and over here. Don't mind the fact that the continents look all wonky. I had to reflect the picture and then reflect all the words back so that you could read them still. But basically what's happening is the axis is pointing in the same direction here and here. What changes is that the sun's rays are coming from the left in June and coming from the right in December. Now it's not actually like left and right per se, but basically the direction that the sun's rays are coming from swaps sides of the planet from June to December, from one half of the year to the other, or from one time of year to a point 6 months away from it. The direction that the sun's rays are coming from swaps sides. So when the axis doesn't move, that means you go from 24 hours of day over here in June at the North Pole to 24 hours of night, because suddenly you've been plunged into darkness because the sun's rays are coming from the other side. So hopefully that clears that up. So now let's wrap this up. I'm sorry this is getting to be a little bit longer than I thought it would be, but let's wrap up. What causes the seasons ultimately? Basically, it's the tilt of the Earth's axis together with its revolution around the sun. Because if the Earth wasn't moving around the sun, then, well, one, that would create a hell of a lot of problems, but two, that one part of the planet would always be tilted towards the sun, and you still wouldn't get any seasons. You just have a hot part of the planet and a cold part of the planet. But so the tilt of the axis, combined with the fact that the planet's moving around the sun, is responsible for the seasons. And you might have noticed, I feel like I mentioned this earlier, but in case I didn't, you might have noticed that the tilt of the axis, the actual angle, the 23.5 degrees, is responsible for the location of where these major circles of latitude fall on the planet. So the axial tilt is 23.5 degrees. The tropics are located 23.5 degrees away from the equator, and the polar circles are 23.5 degrees away from the poles. That is no accident. The axial tilt dictates where the subsolar point can fall, like the area that it's restricted to, and the areas of the planet where you could get 24-hour days and 24-hour nights. So if the axial tilt was different, the locations of the tropics and the polar circles would also be different. So that's just a fun little tidbit there. So what's the relationship between seasons and climate, or like where you are on the planet and the climate? So as we saw, depending on where you are, if you're really, really far north or really, really far south of the equator, you'll be experiencing a climate where temperature tends to change wildly over the course of the year, because in winter you're getting very little sunlight and it's coming in at such a shallow angle that it's not really carrying a lot of heat to your specific area. It's carrying the same amount of heat, but it's got to be spread over such a large area that your individual little, your house or your town or your country, depending on the size of the country, of course, doesn't get that much heat compared to the same sized area somewhere where the sunlight is more direct. So you don't get that much sunlight, you don't get it for that many hours, and it's not very direct. So the temperature gets really, really cold in winter. But on the plus side, in the summer, when your part of the planet is tilted towards the sun, suddenly you're getting this really, really direct sunlight. And so the temperatures can get not insanely hot, not like they get in equatorial regions or tropical regions where there are deserts and things like that, but it does get quite a bit warmer. So like, for example, in my town, I feel like I mentioned this last lesson as well, it's not uncommon for the temperature to reach 32 degrees Celsius in the summer, but it's also not uncommon for the temperature to reach minus 32 degrees Celsius in the winter. That's a 64-degree difference every year. Whereas in other places, in more tropical places, especially near the ocean, the temperature is basically like 25 degrees all the time, all year long. The temperature really doesn't change that much in equatorial regions, and those regions near water, it doesn't change that much. I live very far away from a large body of water that could decrease this temperature gap, and I live far enough north that the gap gets pretty big. So this is not uncommon at higher latitudes, and that leads to a vastly different climate than what someone might experience in a more tropical or equatorial region. So then you get that it's common for snow to fall in copious amounts in colder countries like Canada, Norway, and Russia during the winter months, but then they also get pretty warm summers, whereas in equatorial regions you don't really get those temperature differences. You'll get maybe a wet season and a dry season, but not much beyond that. There's no significant temperature difference aside from extra humidity due to all the precipitation during the rainy season. And additionally, one thing that needs to be considered is that countries that are in the opposite hemisphere to you, so for everybody that's in the northern hemisphere, climates or weather patterns or temperature patterns in the southern hemisphere seem to look a little bit backwards. So if you look at a country like Argentina, which is in the southern hemisphere, and you look at a graph of its temperature over the course of the year, it looks a little bit backwards because we're so used to July being the hottest month of the year, but for Argentina, it's the coldest month of the year. So as an example, I actually have the climate graph of Buenos Aires on the next slide. So you can see here, we're ignoring the precipitation for the time being, but you can see here, looking at this red curve for the temperature part of the graph, that we would be used to in the northern hemisphere seeing the temperature curve look something like this over the course of the year. But in the southern hemisphere, that's not what happens, because for them, the hottest months of the year would be December, January, February, where we're hitting average temperatures of about 24 degrees. But then in July, the average temperature is like 10, 11 degrees, which is much, much colder than those of us in the northern hemisphere are used to for that time of year. So that hopefully explains, this is something that will hopefully help with your climate projects, that this hopefully explains why, for those of you studying cities that are in the southern hemisphere, why the temperature curve looks upside down, if you will, to what you might be expecting. So yeah, just a couple of final notes. I wasn't sure I would mention this earlier on in the lesson, but I wanted to mention it now. The Earth's axis does wobble a little bit, but it's only a couple of degrees, and it's over such a long period, something like 41,000 years or something, that we really can't notice it on the scale of a human lifetime. So for us, for all intents and purposes, we can just say it's 23.5 degrees. So yeah, that's something that's maybe worth noting, but don't confuse it with the axis wobbling causing the seasons, because that's not the case. But because it does wobble a little bit, the fact that the position of the axis relative to the Earth's orbit, because that's how we measure that 23.5 degree angle, we needed to measure it relative to something. So as the position of the axis changes to that plane, all the positions of the major circles of latitude, except for the equator, will also change, because the rest of them, everything besides the equator, its position on the globe depends on the tilt of the Earth's axis. As we saw that the tropics are, the northern and southern tropics are 23.5 degrees north and south of the equator, and the Arctic and Antarctic circles are 23.5 degrees south and north of the poles. So it's all dependent on this number right here. So if this number changes, the positions of all of those, except for the equator, because it's at 0 by definition, the rest of them would all change. And that's something that you can look into or ask me about when we have our next live class on Tuesday. But until then, that's basically it. So there was a lot in that lesson. This has been over an hour, and I kind of suspected it might become that way while I was building the lesson. So absolutely let me know if you have any questions, or if there's something that I left out or something that you'd like to hear more about. We can totally talk about this again. But of course, if I don't hear from you, then I will see you all in the next video. Have a good one.